Now let's see this relation and try to decompose it into Bcnf. So there are various ways of doing it. You can first decompose into second normal form, third normal form, and then into Bcnf, or by using the definition of Bcnf you can decompose it directly. So what does Bcnf say? If you take any functional dependency which is applicable on the relation, only if it is applicable on the relation, okay? If it is applicable on the relation, then applicable means holding. Holding means whatever attributes are there in the FD, they should be there in the relation. If it is holding on the relation, then you try to find out the you try to see that every left side of the functional dependency has to be a super key. If it is not the case, then we are going to decompose the table until we get until we see that all the left sides of the functional dependencies are going to be a super key on the table in which it holds, right? So let's see this with example. Now first of all, as usual, you are supposed to find out what the candidate key is, right? Otherwise we cannot say whether the left side of the functional dependency is super key or not. Now let's try to find out the candidate key for this. Okay, the simplest way is see the right side of all the functional dependencies and then see what is missing in the candidate key. Now if I see it, right side is C, so C is there, and then right side is DE, so DE are there, and then here the right side is F, so F is there, and here the right side is GH, so GH is there, and here the right side is IJ, so IJ is there. Now what are the attributes that are missing in the table? Only two attributes are missing, right? What are they? A and B. So A and B are not being covered by any of the functional dependencies, therefore every candidate key should definitely contain AB. So AB is going to be present in every candidate key. Now let's see if AB itself is going to be the candidate key, which means AB is necessary to be present in every candidate key. Now I want to see if it is sufficient or not. So how can I find out? If I find out AB plus, so it is going to be AB, and because of AB I am going to get C, and A determines DE is there and A is there, so therefore because of that I am going to get DE, and then B determines F is there and B is here, therefore because of that I am going to get F, and F determines GH is there and F is there, so because of this I am going to get GH, and then D determines IJ is there and D is here, so I am going to get IJ. Got it? Okay. Now you can see that clearly AB is sufficient to be the candidate key, right? And so you can say that AB is the only candidate key. Why? You cannot delete anything from this and you cannot get a smaller candidate key, and it is just enough. So if you try to add anything, that will become a super key. Therefore AB is the only candidate key. So you found out the candidate key, right? Now according to this candidate key you can identify whether the left side of the functional dependencies are super keys or not. Now if you see this, left side of this is super key. So clearly this dependency is holding on this relation and the left side of this dependency is the super key. Therefore according to this functional dependency, this table is definitely in Bcnf. But then it is not just enough. Try to find out all the other functional dependencies which are holding on the table. Now what are the other functional dependencies? One is this, A determines DE, right? And B determines F, F determines H, all of them. Now let's try to find whether the left side is super key or not. If you see this, left side is not super key. In fact this is partial dependency, isn't it? But then don't worry about it, because we are not going to first break the table into second normal form and then third normal form, but I just wanted to give you the information. Partial dependency, which means left side is not the super key, therefore it has to be decomposed. And again B, partial dependency, or we can see that left side is not the super key according to the definition of Bcnf, we should break it, decompose the table. And F, again according to the definition of the Bcnf, it is not the super key and we have to break the table. And D, again according to the definition of Bcnf, it is not the super key, so we have to break it. So now we are going to take the table A, B, C, D, E, F, G, H, I, J, and we are going to break it one by one. So now if you see this, because of this, since A is not a super key on this, I am supposed to break it out into small tables in such a way that for the smaller table A is going to be a super key. So find out A plus for that. If I find out A plus, I am going to get A, D, E, isn't it? See, I am going to get A, D, E, and because of D I am going to get ij, right? Therefore make a new table with A as the candidate key and then see what are all the functional dependencies that hold on this. Now for every functional dependency that hold on this relation, the left side should be a super key for that, of this table. Then only you can say that this is in Bcnf, otherwise it is not in Bcnf. Now let's try to find out what are the functional dependencies that hold on this, right? So what is it? So one is A determines DE is a functional dependency that hold on this, and D determines ij is also a functional dependency that hold on it, right? Now if you observe this one is left side of the functional dependency is a super key, fine, but this one is not the super key, isn't it? That is why you are again supposed to decompose it by taking D plus. If I find out D plus, I am going to get Dij. Therefore it is going to contain D, so ij is going to be taken away by D. So D ij is a new table, and what is the other table? A, E is remaining, and let D be there, so that there has to be something between these two, right? So one table is going to be Dij, other table is going to be ADE. Now find out what are the functional dependencies applicable on this. Now if you see this, functional dependency applicable on this is ADE, and sorry, here it is Dij, and here it is ADE. Now clearly ADE, so left side is a super key, so no problem with that. Now if you observe this, Dij and again left side is a super key, so no problem with that. So we have decomposed this table in such a way that these two tables are in Bcnf. Why? Whichever functional dependency holds on this table, for that functional dependency the left side is a super key. If that is true, then the table is going to be in third normal form. Okay, now what are over? So one is, so with A, D is taken away, E is taken away, and I is taken away, and J is taken away. Got it? Okay, now this one is taken care of. What about B? Again this one holds on this. See what is remaining? B, F, G, H, isn't it? Now this one is holding on this, and again this is not the super key on this. Therefore what are you supposed to do? Decompose by finding out the closure of the left side. So what is closure of the left side? B plus equal to BF, and because of F I am going to get GH, right? Therefore from this B is going to take away G, F, G, H. See, whenever A is going to take away some attributes, let A be there, and whenever B is going to take away some attributes, let B be there. Whatever is remaining will be with those, so that you have to maintain always common attributes. See, for this entire thing the common attribute is A, and for this entire thing the common attribute is B, so let it be there. Okay, now what about this B, F, G, H? Now let's see what are the functional dependencies that hold on the newly formed table. In this table B is the candidate key, isn't it? Why? Because B plus gave me all this. Now what are all the functional dependencies that hold on this? One functional dependency is B determines F, and other functional dependency is F determines GH, right? And now if you see this one is according to the Bcnf, left side is the super key, and so not a problem, but this one is creating the problem. Why? Left side is not the functional, this super key. Therefore decompose this table in such a way that this left side is going to be a super key for one of the tables. Now if you find out F plus is going to be FGH, right? Now what happens to here? It is going to be FGH in one side, so F is going to take away GH, and then let the F be there, so that it is going to be the common attribute for these two tables. Got it? Okay, now F is going to be the super key for this, candidate key for this, and the only dependency applicable on this one is this one. And if you see this, the left side of the dependency which holds on this is a super key, and so this is in Bcnf. Got it? Now what about this one? B determines F, right? Now if you see the left side of the dependency which is F, so in this table F is the candidate key. Now only dependency that holds on this table is B determines F, and if you observe it, it is the left side is the super key for this table. Therefore this table is in Bcnf, right? So this table is in Bcnf, this table is in Bcnf, and these two are also in Bcnf. Now what are the only remaining attributes? A, B, C, isn't it? A, B, C. So let AB be the key, because this one is already there. Now if you see this, the only dependency which holds on this is this one. Got it? Now if you check this, all the tables which we got are containing all the attributes which are originally there in the table, and we have also considered the functional dependencies which are applicable on these tables, and we have made sure that every left side of the functional dependency is a super key for that table. Therefore these are all the tables which are formed after decomposing into Bcnf, right? Now if you observe it, the way we split, so while splitting them, either we have split them according to partial dependencies or transitive dependencies, even though I didn't mention them explicitly, right? So the other way of solving this one is try to break the table into second normal form by seeing the partial dependencies, and then into third normal form by seeing transitive dependencies, and then come to Bcnf. You are going to get the same answer, right? So this is the answer anyway. Okay.